Dear 10th class students, our next point of discussion is number of tangents from a point in the plane of a circle. So, in the plane of a circle, there is a point, means it may be interior of the circle, it may be on the circle, or it may be outside the circle, but still it is in the plane of the circle. So, in the plane of the circle, if there is a point, okay, how many tangents can be drawn from it? This is the main important question now here. How many tangents can be drawn? See, this is center, say, center of the circle. See, now I am taking as a first case, as case 1, what I am doing is that I am taking that point P as exterior point of the circle, okay. So, if P is exterior point, if P is exterior point, if P is exterior point, right? Then how many tangents you can draw from point P to the circle? If you see that, it is clearly visible that there exist only 2 tangents from an exterior point to the circle. So, so 2 tangents, number of tangents that can be drawn from an exterior point of the circle is 2. Understood? So, if a point P lies outside the circle, okay, total number of tangents that can be drawn from the point P to the circle are 2. Understood? Now, what is case 2? If P is the point that lies on the circle, P is a point on the circle, so if P, the point P is exactly on the circle, so like this, how many tangents you can see that P is exactly on the circle? So you can see only 1 tangent can be drawn from a point P that lie on the circle. So number of tangents that can be drawn from the point P on the circle is equal to 1. So now as the last case 3, if P lies inside the circle, so that P if is lying inside the circle, so how many tangents can be drawn? See, like this. So if P is lying inside the circle, so how many tangents you can draw? See, of course, this is not. See, if that point P is lying inside the circle, any line through the point P, okay, it cuts the circle, so it cannot be tangent to the circle. So if the point P lies inside the circle, any line through the point P cuts the circle at 2 different points. So in this case, number of tangents is equal to 0. Understood? So, dear students, our next theorem is tangents drawn from an exterior point of a circle are equal. So, this theorem is giving us the information that from an exterior point of a circle, if you draw tangents to the circle, so those two tangents are equal in length. That's what this theorem is saying. They are equal in length. So, these are radii, and you know that radius is perpendicular to tangent at the point of contact, because just now we have proved that theorem. So, say A, B, P. Okay, this is center. So, what is given? P is exterior point of the circle. PA, PB are tangents. This is given. What is required to prove? The tangents are equal in length. PA is equal to PB. So go for construction. So in construction, what you do is draw a line with joints P to C. So join P and C. So now proof. Say this triangle you take, and this triangle, there is right angle. Okay, you are seeing right angle, right? And this hypotenuse is common. Hypotenuse. These two are radii. Radii are equal. So RHS congruency formed. So what is proof? In triangle AC, in triangle PAC, in right triangle PAC, and in right triangle PBC, in triangle PAC and in triangle PBC, okay, there is right angle. Angle PAC equal to angle PBC, and each equal to 90 degrees. Each equal to 90 degrees, right angle. And hypotenuse CP is equal to CP, hypotenuse, and CA is equal to CB, radii of the same circle. Therefore, right angle hypotenuse side congruency is formed. Therefore, by RHS congruency, you can conclude that these two triangles are congruent. So, triangle PAC is congruent to triangle PBC. As the two triangles are congruent, by CPCT, you can conclude that PA is equal to PB by CPCT. Hence, proved the theorem. So, thus, tangents drawn from external point of a circle are equally successfully proved.